Hello and welcome back to a new video where we talk about today for the interfaces. Could be civil, could be mechanical, could be piping or electrical or INC. It's always a nightmare and the devil in the details. It's always a problematic issue when we talk about EPC and engineering stage. For INC, today's systems provide you with a lot of communication options. This put a lot of pressure on the INC to integrate and to do a lot of system integration and moving data between systems. Today, we will talk about the interface and how to make an effective and hopefully successful project and easy. So what we will do today is to talk about stuff which is not having a remote I/O. So remote I/O are not included in our video today. If you have one vendor providing you with a lot of the system, but it's all come from one vendor, let's say one DCS supplier and one system, then probably we will not talk about it. Same if your system does not have any communication port, then we don't talk about it. The more I/O you have, the more relevant to this video actually, and the stuff which is you need to a lot to discuss. The other thing is that the more repeated items in the system, and that would be ideal for our video really. So the steps will go through main 3 steps. The first one is to define, and then we plan, and then we execute our project. So the first thing is we will talk about defining your system, assuming you have a DCS, PLC, HVAC, UPS, weighing system, SCADA, RTUs. So those are a lot of the system which is you can find them today. So they will talk to each other, communicate, and move data between each other. For the sake of our video today, we'll call them, one of them is remote and one of them is local. Regardless of your system, talks to about 10 or 15 or 100 of another system component. At the end of the day, we have system 1 is communicating to system 2. System 1 is connected through hardwire, input-output to your machine or your process. In this case, system 1 is local for this process, and system 2 is considered as remote for this process. Also for this process, if this system 2 have the I/O and connected controlling this process, we call this one is local for this process, and system 1 is remote for this process. First thing in the defining scope, definition is we need to define our scope. So what we need, you have to bring all your documentation together. Like the first thing we have is a code and a specification, P&IDs, cause and effects, narrative, etc. Those, all the data which is you need to design your system, so you need them to be ready. You have to set with the operation. INC, no matter what good you are, operation and process are the user of the system, and they have to give us what they really need from the system. So with the P&ID and logic, you can understand what they want to do, what kind of data you want to move, and their expectation to control or just monitor, and so on. So if we can look at all the stuff which they talk about, and then we say this is those items that we need to do, and those items maybe we will put it as an optional, and some of them is not achieved. The way why it's not achieved, maybe the unit does not have communication or cannot communicate with our system right now, so maybe we'll call it a challenging instead of unachievable. But some of the stuff actually we cannot because of the distance, or anyways, at least this is something you have to put it in mind, because this video is a general, so we'll just put them as here. One of the very crucial item is where you will put your logic. When we said local and remote, this is very important, because in my point of view, you should not have any logic which associated with safety related to personal or equipment protection. You should not put it in the remote system. Because if you lose communication, regardless if it's redundant or not redundant, if you lose communication, what the local system will do, you have to know what will happen. A lot of the time, we don't put any control logic in the remote. We keep it all in the local. And also you have to define how you will start a big machines. Like if you have a compressor, do you allow the remote site, like the DCS, to stop it, or somebody has to go around the compressor, make sure everything is fine, and then locally start it only. So this is stuff which is you need to discuss with the operation before you go ahead and design your interface. Now this slide, actually I tried to make it as complicated as I could, but it is really, it is not that complicated. What's happened is that if you look at one of those machines or process, you may have, let's say, a big skid or a small skid, regardless. If you have a barge or a dredge or a piece of equipment, this piece of equipment, they want it to be under control from local or remote, or local and remote, or you can share some of the control and allow the local to do a lot of things and prevent the remote from doing some stuff. So this is for control function. You can put it in 3 categories: full, shared, and none. And let's say the local will have full control of everything except the time synchronization, but the remote will have full control on the time synchronization. The remote will have none on the historian or the maintenance, and so on. So this is just an idea when you design your system. How those two systems would communicate with each other? They communicate through a media, or let's say an Ethernet or RS485, 232, fiber optics. This is the mean, which is the pipe which is you put your data through it. Now the data can come onto as the protocols which is you're using. 99% it would be the MODBUS. This is the first option for everybody. Everybody now has mainly MODBUS. Other protocols are available. Think about it. It's well proven. You can have easily a simulator. You have a lot of stuff can work as a master slave in MODBUS, or you can also have a client server. Those techniques, maybe we just put them here, but reality is sometimes you'll find your system is working as client server or master slave at the same time. You think about the redundancy required. Do you need redundant communication, or you don't need a redundant communication, and so on. You can look at your available port and if you need an extra port. We're still in the planning. We said that we try to find a way to make one item which can serve many purposes, which is we need to go with cookie cutter approach. So you look at your PNID and see how many analog indication only you transfer between the systems. Some of them has alarms, some of them does not have alarms, but it's better to arrange all of them as having alarm. Then you can add or remove the alarm as needed. And also see how many PNID loops you have. How do you have any on-off valves, motor MOVs, and so on. And then you can still keep adding as you go. Even if it's only one piece, then it's better to put it here now. If you have a machine, then you can look at the machine as you have sensors for statuses, you have measured variable pressure, temperature, and so on. And then you have stuff you running like motors and solenoids, and then operating parameters and so on. So you put them all in some kind of a list, and then from this list you start to build a block which represent all the data you need to transfer between those two systems. The idea is cookie cutter or build one to serve many purposes. The first one, we will go through it a little bit. The rest will be, you get the idea. Let's say for analog input data exchange, the first thing you will send the variable itself. Then you say, okay, it's real value. Maybe it's integer. It's how many bits you can look at the two system and what the data you're transferring. And it's better to put it here in your table. What is your low limit and your high limit? Because on the DCS, you will have a faceplate which shows the analog input. So you need to scale it. The set point for the alarm, you can see that the remote will read it, will not change it, but only will read these values. Then you have all those high alarm and high alarm, low, 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 and they are come as a bit, but it comes on one register, integer 16 bit, and then you can assign every bit for one of these. It's very important at this stage to define the status of the bit. Let's say bit 0. If it is 1, that means it is tripped. If it is 0, it means it's normal, and so on. So you define these things. So up front, nobody comes and asks you later. We keep some of them as a spare because you have 16-bit. Then you have some free data in this form. You can see now we moving everything as a register. We don't use it as a coil or something on the MODBUS. That will give you more flexibility. You have to, at this point, you make sure that you're transferring the numbers between the two systems in a way they understand it and they correctly read them. Because sometimes you have this IEEE format, you can have this integer, they cannot unsigned integer, signed integer, and so on. So at this stage, it's very important to identify these things. And this means it's very important. Now, this is another form of how to build one serve menu. You look at your, let's say, on a valve MOV or something. In the local, like assuming it's a PLC, you have a function block which is controlled this valve, and even you have only 4, maybe 5 open, close, stop, open, close statuses from the valve. The function block may generate more data, like the valve is closing, the valve is opening, valve timeout error, and then it receives the open and close command from somewhere. And based on you are in the local or remote mode, then the open and close command actually comes from the local HMI or the local logic, or it comes from a command from your remote system. So your logic will define where these data comes from, and in all times, let's say the display will go to both systems at the same time. So now you build, once you understand what's going on, you build all the table which is required to operate one MOV. We agree on the data, and then we go ahead and build our system. Similarly, if you have a PID loop, you go through the same exercise. The only thing is that you have to think about it is, let's say, set point. Set point can come from local or remote. When you are in local mode, the remote actually reading your set point only, but it cannot write in it. Now, when it is in remote, the remote system will write in your set point. So the system should allow maybe read and write in 2 different registers for the set point and so on. So that's again based on the programmers on both sides. Again, you will have a lot of data, and you can see read, write here, and so on. So the next step in the planning is to make sure that the operator, when he moves between the systems, he would see and feel almost the same thing, like the color of the background colors. Pump here, if it is running, it is green. If it is stopped, it's red. So let's agree on those now. This is the shape of valve, this shape of pump. You may not be able to do it exactly the same, because of course the HMI on the PLC is different than the HMI on the DCS, but you may be able to make them a little bit closer to each other. Make sure that you're using the same abbreviations. Here is some tips. We said that your system should be able to recognize there is a failure in your communication. This can be very easily done by one system is reading the clock, the seconds of the clock of this other system. And you expect that this thing goes from 0 to 60, back to 0, up to 60. And when it looks at this value in its register, if it doesn't change for 5 seconds, that means the communication is lost. Other ways, there is many ways, but there's other ways, like the system actually write in its own register a value, then the remote will write on this value, erase it and put something else. So if it doesn't change, meaning there is no communication. Data compact, they don't send data, let's say in coil phase, just put them into register. Then when they move to the other side, you can fan it out and spread it again. So let's look at one example here. If you have, let's say, a machine and you start the machine. So the machine is waiting. You send one register, and this in the register you have numbers. The numbers, each one represent a status of this machine. So let's say it's 1 is waiting for start, 2, and so on. Now you can do the same thing through bits. So if you say 16-bit, you can, if bit 0, the first one is 1, that means it's waiting for start. Now this machine is in warm-up. So again, sometimes it's preference, sometimes is how easy it is. The other thing is here is use separate data blocks. Don't mix the read and the write. Try to put them in a separate places and consecutive registers. So it's make easier for the communication, and actually this is optimizing the communication between the two systems. There is other tips, like if your system, let's say the PLC cannot send signed integers. Sometimes we face it actually in one of those small temperature trip systems for the VFD. It cannot send signed integer. So what the system does is it always add, let's say 200 to the value, reading the value of the temperature. Temperature is minus 50 maybe to plus 100. So always they added 250. So you receive at the other end the temperature scaled up with plus 150. So you just, or 50 or 250, and then you subtract the value, you get it. If a system cannot transfer except integer and you want to send something, you can multiply it and you get on the other side, they scale it down. So in the planning, try to make it simple. So if you can make it repeated but simple, verified solution, then it's much better than it's one complicated solution. So try to make it simple for everybody. Now, it is a good idea, and it's very important. And once we agreed on all these things, and before you go ahead and design everything, the interface, I do strongly recommend that both party goes back to their office. Each one develop one typical for each one of those systems. one valve, one PID, one whatever analog indication, and then you bring your PLC with an HMI and connect it, let's say, to your DCS, and test this simple PID loop. See if it's working or not. Do you need extra bit for releasing the control and releasing the whatever? Try to see if how you acknowledge the alarm. Do you acknowledge the alarm in this DCS? How it happens in the PLC? Once you tweak those sort of stuff, you tweak it a little bit, then you can now go ahead and build your system. This will make everybody's life easier. Both parties goes to their offices, they try to finish the design, keep the changes to the minimum, and try to make it in steps, not every day a change. And also somebody, maybe APC or the owner, will take control of the communication between parties, and also try to make one point of contact in each place, so you don't have everybody talking to everybody, and you will lose actually tracking of everything, of the changes. Once you complete the system, it's a good idea, or it's a very, very good idea to have your PLC, maybe only the CPU, with a software which simulates your process I/O. And if you look at this part, this is how you verify your PLC program itself. So before you do the interface, I would assume that you already had verified your system. Your logic is working. Then the same software, which is you use it to simulate your process I/O, and you tested your system. Now we use it to connect it to the DCS, and we'll go from far end to far end. So you click on the simulator and make the valve open. You can see it on the HMI. You can see the valve open here. You close the valve from the DCS. You can see the valve command goes all the way out. So now from far end to far end, test had been done. Now you can send your software to the site, because now everything had been verified and complete. So in conclusion, what you do is you prepare the template, you test the template, and then you go ahead and configure, and then you test the configured system. Who is going to do this? Mainly you need one party which is control all of this stuff, or initiate and arrange these the communication. If you let the vendor say, okay, they communicate with each other, they will keep it to the minimum, because they have a scope, they have to finish it, they have other stuff. They always put the interface to the far end, and later we will do it later. We will after we finish. And this other thing is, sometimes they said, what we cannot do the interface. We have to program our PLC before we do the interface. But if you actually build those typicals, then you're almost now halfway through. All you have to do is, now once you agree on all this stuff, you can build your system easily, because we know the kind of data will be transferred, and this have nothing to do with your logic on the PLC. By this, we concluded our video today. I hope it's been good and adding a new information to you. And thanks a lot for watching, and see you in the next video.